All right, good morning, everybody. So bright and early here on November 13th, wanted to do a follow-up video related to the video I did on quantitative STEM and EDS, and specifically dealing with error analysis and some other good questions that came out of that video. So put together a short PowerPoint presentation to do this. And first of all, I want to thank everyone for all of the support for the channel. It means a lot to me. I didn't think it would take off the way it has. Apparently word's really getting around. People talking about it at the microscopy and microanalysis meeting, which is great to hear. Hope to get to one of those eventually someday. I've actually never been as of this point. But thank you very much for all the support. It's really what motivates me to continue doing the videos. And yeah, I apologize I can't do them as frequently as I would like to, but it's kind of tough to fit it in with with the demands of my my position. So anyway, what we're going to talk about today. So we started off in the presentation about the quantitative STEM-EDS. And again, if you haven't seen that video already, please go watch that first, or else this one's probably going to be a little over your head. But we started out with this equation, the Clif-Lorimer equation, okay? So the ratio of the atomic fractions of two elements is equal to the ratio, or I should say quotient technically, of the net counts of element A divided by the net counts of element B multiplied by a sensitivity factor KAB, and this is the Clif-Lorimer equation, okay? You can also, so this is, again, the ratio of the atomic fractions. If you do some math, you can easily rearrange this, and you can get the absolute atomic fraction. Again, assuming we have only two elements, right? We're only assuming A and B. You can get the fraction of A as this, and the fraction of B as this, okay? Right? And you can see if I add the fraction of A to the fraction of B, I get 1, right? As I would expect, okay? If we have a generalized number of elements, right, big N, which I'm denoting here, then this is what we have here for the atomic fraction of element I. Okay, so you have net counts of element I divided by the net counts of element I plus the sum of the net counts of all the other elements divided by the Kij sensitivity factors. And again, now we're doing the sum not over J equal to, we're doing the sum over N minus 1 terms, right? Because we're excluding the J equals I term, okay? You could also alternatively write this as the net counts of I divided by the sigma A omega epsilon product for I, which we're going to get into here in a minute, divided by the sum of the net counts of all the elements divided by, so I should say, divided by the sum of the net counts for each element divided by the sigma A omega epsilon J product for, again, each of the constituents, okay? And that would be a summation over all N terms, okay? And this was the, what I gave the name when you have the I net divided by the sigma A omega epsilon product, I called that corrected, okay? So the corrected counts of I divided by the sum of the corrected counts of all the other elements, okay? And again, this is the Clif-Lorimer analysis, and I do want to stress this is valid only for STEM-EDS, okay? This cannot be applied to SEM-EDS because the way EDS works in an SEM as far as quantification is fundamentally different, okay? Because you're not dealing with a transmission technique anymore, okay? It's considerably more complicated to talk about quant in SEM-EDS, okay? So that's just a reminder, is we're specifically limiting that to limiting this to STEM-EDS, okay? So we have this, these fairly simple equations here for the atomic fractions. What we want to know is what is the error, okay? So the delta in the calculated values here, okay? And that's what we're going to get into today. So here is your typical EDS spectrum. So you see, right, we have a series of peaks here on top of a background. So the spectrum is the red line, and the calculated background is the green line. It might be a little tough to see right there. You can see we have a massive range in terms of the peak intensities here. The peaks in EDS are very, very well modeled as being Gaussian in shape and distribution, which is important when we talk about calculating the spread in the peaks or the error in the peaks, which we'll get into here pretty shortly. Okay, so first thing we have to do, right, is identify the peaks that we want to include in the quant. Okay, so I'm just going to use these as an example here for what we do in the next slide. Okay, so we have aluminum K alpha, calcium K alpha, and lanthanum L alpha here. Okay, so the first thing we have to do is talk about or compute the net counts for each of the peaks. Okay, so what we have here is basically close-ups of each of those three peaks. Okay, so you can see I have, again, the red line is the spectrum. Okay, but then you can see underneath that I have bar versions, right, of the plots. Okay, so I have the contributions from the background in blue, and then what's called the net spectrum in green. Okay, so if you take the spectrum and subtract the background, you get the net spectrum. So that would be the green portion right there. Okay, so you can see, right, there's a big range or big dynamic or big difference in count range for each of these three peaks because obviously they have different constituent quantities. Okay, so that's the first thing, right, is we have to subtract the background to get the net spectrum. Okay, and then what we have to do is we have to compute the full width half max, which is easy to do. Okay, so we figure out the max of the net spectrum, right? We figure out the half and the full width half max of that, which is easy, right? So you can see pretty clearly looking at all of these, right? So the peak of the net spectrum, right? And then if you take half of that, so that's where the plots end, right? As far as the left to right range. And then what we're doing is we're summing the counts over all the channels that fall within the full width half max of the peak. Okay, so within the EDS spectrum, you have individual channels, which are depends on what's called dispersion. It might be 5 or 10 electron volts, depending on how your detector is set up. But basically, each one of those channels has a number of counts, and you're summing up the counts in each channel within the peak full width half max. Okay, again, the net spectrum. This is how we get net counts. Okay, so now we can return to this thing called the sensitivity factor, KAB. Okay, so KAB, when you distill it down, is the ratio, or again, I should say quotient of two sigma A omega epsilon products. Okay, so if it's KAB, we have the product for element B divided by the product for element A. Okay, and then what's interesting, though, right, very obviously, is if I want to figure out KBA, I just take the reciprocal of KAB, right? So KAB is really two sensitivity factors in one, okay, because it describes also the reverse or the reciprocal relationship, right? So this is useful, as we're going to see here in a minute. So again, right, so we have I say 4 element specific parameters. Technically it's 8 because you have 2 elements there, okay? But you have sigma, which is the shell ionization cross-section, depending on the shell for the element. You have A, which is the electron transition probability. So once you cause the ionization, what electron transitions down to fill the hole that generate, and then the X-ray, and that is then generated. Then you have whoops, went a little out of order here. Then you have epsilon, which is the detector efficiency, right? And this is based on the X-ray energy. So the EDS detector does not detect all the X-rays with equal efficiency. There's a, kind of an upside down bathtub curve that we kind of saw for that. And then the last one is the fluorescence yield. Okay, so every time we get an ionization, we don't always get an X-ray out. Okay, so that's what we are accounting for with omega, is the fluorescence yield. Okay, again, I go into more detail with the guts of this in the video on doing quantitative EDS, so I'm not going to belabor this more than this. Just wanted to do a little review here. Okay, so some other interesting things about KAB. So if this is KAB, we have the product for B divided by the product for A. If I take the numerator and the denominator and I multiply each of those by the reciprocal of the product for element C, right? I basically just multiplied everything by 1. Okay, what I end up with here is the sensitivity factor CB divided by the sensitivity factor CA. Okay, so the reason this is useful is if I don't have the sensitivity factor KAB, but I have KCB and KCA, I can get KAB. Okay, so I don't have to go and actually calculate or measure KAB if I have these other two. Okay, so if we can use silicon titanium as an example. So I don't know if there's a material, right, that we could use as a standard for this, which we'll get into here shortly, that contains a known compound with a ratio of silicon and titanium. Okay, but we have oxides of these. Okay, so we can do, divide the numerator and denominator through by the product for oxygen. Okay, and so then we get the sensitivity factor KO titanium and KO silicon. Okay, so, and this is useful, right, because, and this is what's commonly done, is that you have oxides for a lot of elements with known compositions, right? AO, AO2, A2O3, this kind of thing. Okay, so it's very easy to calculate sensitivity factors for other systems, right, that are not oxides by just using the ones for the oxides. Okay, so we saw an example here. You can use silicon dioxide and titanium dioxide to calculate K silicon titanium. All right, so now we're going to get into the error analysis part. Okay, so before we get into the nitty gritty here, we want to just go over some basic error analysis rules. So we have the three relationships on the left here. So if we have a sum of quantities, right? S is the sum, quantity is Q. Okay, if we have a sum of quantities, the square of the error in S is equal to the sum of the squares of the error for each of the individual quantities. Okay, that's what we do if we have a sum. If we go down to the next line, we have products and quotients, right? So I have 3 here as an example. It's a little more complicated. So what we have here is delta S divided by S is equal to the square root of the sum of the relative errors of each of these quantities. Okay, so when I say relative error, when you have delta Q divided by Q or delta S divided by S, we can call that a relative error, right? Not an absolute error. Obviously, if we multiplied through by S, we would get an absolute error, right? Delta S, okay, which could be done. So this is what we do if we have products and quotients. And then if we have something that's kind of a mix. So what if we have a sum of products and quotients? Okay, so this is a little more complicated, but what you end up getting is this. Okay, so your delta S squared, right, is equal to the ratios, or in this case, right, you could use it as a product to have it as a quotient here. The quotient squared, okay, for component I, and then you're multiplying by the relative error of component A squared plus the relative error of component B squared, and then you're multiplying that by the quotient squared. Okay, and then you're summing up all of those over your n terms in the sum. Notice that I use little n here and not big N, right? Because we're denoting that this is not the number of elements per se, just number of components in the sum here. Okay, so these are the relevant mathematical operations in quantitative EDS. Last thing to point out here is I have delta I net. So we talked about the net counts. So there's an important relationship here for the delta in that. Okay, because it's Gaussian in distribution, this is what you get. okay? Without, it's a little bit hand waving here, but you have 3 times the square root of the total net counts, okay? And this is important. We're going to see this a lot here, okay? So now if we want to generalize the error for an element I for if we have n elements. So this is the original equation on the left, okay? And we can simplify this by reducing the denominator to I sub I net plus S, right? Because we have a sum, and then we can call I sub I net plus S equal to D for denominator, okay? So what we do then, right, we use the rules that we have. So the relative error is equal to the summation and quadrature of the numerator plus the denominator, which is the same thing as saying the sum of the squares and then taking the square root, okay? Right, then we can substitute in the relationship for delta I sub I net, okay? And then now we need to expand on the delta D divided by D, okay? So delta D, right, because D is the sum of I sub I net plus S, okay? So we have 2 terms that we're summing, okay? We can again expand delta I sub I net as the 3 square root of I sub I net, and then we have the delta S squared in the summation term, okay? So then the summation term error squared is this, right? So again, we have a sum and quadrature here, okay, of the individual errors associated with those quotients, okay? And so this is what we end up getting ultimately, okay? So you can do the math and compute this all out, okay? So, right, ultimately we make the substitutions there. We substitute in for delta D divided by D, okay? And then finally what we end up with is this equation, okay? Which is, you know, kind of complicated, but it's really not that bad, okay? Really not terrible. But this is the calculation for the relative error of element I, okay? And as we can see, right, this depends on the net counts in the peak for element I, but it also depends on the net counts in the peaks for all the other elements, right? Because you have this summation term in the denominator for the second term, right? And it also depends on the Kij sensitivity factors for all the other elements as well, okay? That are involved in the quant, right? So again, you know, we could have 2, we could have 3, you know, whichever is in there, okay? And so the last thing I want to draw your attention to is this guy right here, right? So this is where we see the error in delta K come in, okay? So this is, right, this was one of the questions asked, like, how do we figure out the error in the sensitivity factor? Like, where does this come from? Okay, so this is where it factors in here mathematically, okay, is the error in delta K, which we're going to get into here, okay? Again, because the peaks are Gaussian, the delta I sub I net is given by 3 times root I sub I net. Okay, so we have n-1 delta k ij values as the other sources of uncertainty, okay? Aside from, you know, the ones related, okay, as the other sources of uncertainty, right? Because we're not accounting for the uncertainty in the other peaks. We're only accounting for the uncertainty in the I sub I peak, okay? So now the question is, how do we determine delta k ij? Okay, so if we're going to simplify this for just 2 elements, right, this is pretty easy. You can, you know, do this pretty quickly. You get the expression for element I, the expression for element J, okay, and then this is the equation that you get for delta I, for the relative error for element I, okay, right? This is very simple because we have only 2 elements, okay? And again, that's the component right there. So we only have 1 delta K term that we have to worry about. So we have to determine Kij and delta Kij, okay? So there's 2 approaches to doing this, okay? There's the experimental approach and the theoretical approach, okay? So the experimental approach requires that we have a standard sample with an accurately known atomic fraction of element I to element J, okay? So we need to have this in order to do the experimental approach. Okay, so we basically measure I sub I net and I sub j net n times, okay, and the more the better, right? So the more counts, the better, and the more times we measure, the better, okay? So K sub Kij is calculated for each n measurement via the Clif-Lorimer equation, right? It's very easy to rearrange the Clif-Lorimer equation and calculate Kij in terms of I sub I net and I sub j net and the atomic fraction ratio, okay? So then what we do, because we have n measurements, is we compute an average for Kij, okay? And then delta Kij is the uncertainty in this average calculation, which can be done mathematically, as we're going to see here in a minute. The other approach is theoretical, okay? So we calculate Kij from first principles, which was what we went over in the previous video on quantitative STEM-EDS, okay? So then the error in Kij reflects the uncertainty in the parameters used to calculate it. Okay, so then there's 8 parameters for each Kij term. So you have 4 for element I and you have 4 for element j. So we have the error in the ionization cross-section, the transition probability, the detector efficiency, and the fluorescence yield. Okay, so those are the 8 sources of error that we have to account for. Okay, so the experimental approach, we measure Kij via a standard. Okay, so this is the standard equation for calculating an average, right? You can see this is basically just a reworking of the Clif-Lorimer equation where I'm summing the ratio of I sub I net to I sub j net over little n measurements, okay? So I'm doing that little n times and I'm getting an average, okay? Very simple. Okay, so then I can use that equation and all the relationships we had for extrapolating error based on summation and products and quotients, and I can get an expression for the error in the average Kij. And this is what it looks like, okay? So what we see here, right, and then again, we can simplify this because we know what delta I net is and delta I sub I net. Sorry, I missed that apparently in that second term there. I put it in the bottom one though. Okay, but we can replace delta I sub I net and delta I sub j net with 3 times root of I sub I net and 3 times root I sub j net. Okay, so that's our final equation for the error in the average measured value of k sub ij. Okay, so to get a small, right, delta k sub ij, it's very obvious here, we need to collect a lot of counts. Okay, the more counts you select, the more those error terms, or I should say, the more those terms in the under the radical go down, right? So we can see we have root I sub I net divided by I sub I net. Okay, so that reduces down to, right, 1 over root I sub I net. So we can see very clearly as we get more counts, that term is going to trend towards 0. Okay, so this is why you need more counts to get more accuracy in your quant. Okay, so collect a lot of counts, get a lot of counts in your peak. You might need to count for a long time, right? Especially if your standard has maybe a ratio that's not particularly close to 1, right? One is much smaller than the other. The other thing you need to do is do a lot of measurements, right? So the more measurements you do as well, because we have the 1 over n term there, okay? So that also helps you out too, okay? So you collect a lot of counts in your peaks and you perform a large number of measurements, okay? That's the experimental approach, okay? So the advantages of this is accuracy, okay? Again, if you collect a lot of counts and you perform a lot of measurements, okay? We don't have to rely on parameters of questionable accuracy, right? We don't have to look up, data on fluorescence yields and ionization cross sections. That's all irrelevant, okay? Right? We don't need to know any part of the sigma A epsilon omega product for any of the elements present, okay? But disadvantages is we need a standard, okay? We need a standard with a known composition, and maybe this isn't possible depending on your material, okay? But of course, as we saw, right, if we have 2 other materials, we could potentially use those, right? We could use those to reverse calculate the sensitivity factor that we're trying to get, okay? And this is obviously very inconvenient, okay? So you have to first make a sample of a standard. Maybe that's easy if you have like nanoparticles for your standard. If you're talking about a lamella, well, that's a pain, right? Because you have to go fib out a lamella, okay? So that's time consuming to maybe just to make the sample, but then you also have to collect a lot of spectra, okay? And each spectra you might have to collect for a while too, okay? So time consuming, you then have to, obviously crunch the numbers and analyze the data as well. You also have a lack of transferability, okay? Your results are only going to be valid for the microscope that you are working on, and it's also only going to be valid at the voltage that you are working with as well, okay? So you have a lack of transferability with the experimental approach, okay? So the next thing then is the theoretical approach, which is you calculate K sub ij. So this is K sub ij again. We have the sigma A omega epsilon product for J divided by the same product for element I, okay? So if we want to compute the relative error in K, we have the summation and quadrature of the relative errors for the product for element I and the product for element J, okay? And then we can further simplify this, I shouldn't say simplify, but expand into this, okay? So we have 8 terms under the radical now because we have 8 individual terms, right? So we have 2 sigma products, 2 sigma values, 2 A values, 2 omega values, and 2 epsilon values, okay? So this is what we ultimately get for the relative error in Kij, okay? Again, if we're taking a theoretical approach, okay? So now we have to determine errors for each of these terms, right? And this is tough to do, okay? So some of these are calculated values, right, or calculated theoretically. So we don't really have errors for them, right? We have to make, kind of some educated guesses, say maybe it's like 5–10%. Some of them we don't know, okay? So this is what we often do here with this is we make some educated guesses for the relative errors, right? We say maybe like 5 to 10%. But this is, one of the issues with this, right, is because some of these values are theoretical, then, we have to do some estimating here, okay? So the theoretical approach has advantages, right? So it's more convenient, okay? It doesn't involve making lamellas. It doesn't involve collecting a lot of data, okay? So we have convenience on our side. We don't need, special materials, right, standards, any of this. And it is more easily applicable to other systems and voltages, right? Because all of those parameters can be easily calculated for other voltages, although strictly speaking, the only things that depend on voltage, I believe, would be the ionization cross-section. The one exception to this, of course, is your detector efficiency. So that is not obviously, that is detector specific, okay? So if you go to a different microscope with a different detector, your detector efficiency curve is possibly going to be different than yours is, okay? Even if they're both STDs and they're both windowless, I wouldn't assume that they're all going to be the same. All right, disadvantages. So the biggest disadvantage is the accuracy, okay? Because, we have these uncertainties in the sigma A, epsilon, omega terms. We don't really know what a lot of them are. We can assume that they're, probably pretty large and they're also fixed. So it's not something where we can do a bunch of measurements and drop the error like with the experimental approach, okay? So we have basically like these fixed errors here that are, larger, I would say, right? And we really can't do anything about, okay? Again, we're relying on theoretically calculated values in some instances. Some of the data is not theoretically calculated, okay? Like the fluorescence yields, there's data available on that. Even that, though, you can question how it's collected. You can question its accuracy. But again, right, some of it, like the ionization cross sections in particular, those are basically, theoretically calculated, okay? So again, we're usually just estimating error for those. And then we also, right, we need to know the detector efficiency curve, right, very accurately, and this is not transferable to other detectors, okay? That's limited only to our specific detector that we're doing on our specific STEM, okay? All right, so just to summarize here, we went over the origin of Kij, right? So where is Kij? How do we calculate it? We saw the two approaches, the experimental versus the theoretical approach for dealing with the sensitivity factors. And then we went over the error calculations in the quantitative results, right? So we have the two sources of error, right? We have the error related to the counts, right? The net counts, okay? And we have the error in the sensitivity factors, okay? So those are the two sources of error. And depending on how we do the measurements, right? If we're doing an experimental versus theoretical approach, our delta Kij is going to be different in both of those scenarios, okay? Right. So if you have, of course, questions or comments, please feel free to leave a YouTube comment. I would prefer that so everybody can kind of see it and benefit from it. You can also email me directly. I know there's people always finding me on LinkedIn, so please feel free to look for me there. And once again, thank you for all of your continued support, and hope to keep growing the channel. So with that, I hope you have a good Monday and look forward to seeing you all again very soon.